Welcome Dr. Lutz and Dr. Shi. My name is Connor Purvis, and for my final individual presentation, I'll be presenting on our group's Smart Ankle Trainer and the progress that we made throughout the semester. Just a quick overview for this presentation, I'll be talking about the project background and how the initial problem came into scope. Then I'll be talking about how our team utilized brainstorming to combat a lot of the issues that were apparent in the initial problem. Then I'll be going into our 4 original prototypes that we presented at the midterm presentation to JUMP in order to get their feedback on what they thought was best. Then I'll be going into the midterm presentation itself and how our group was able to utilize a lot of the feedback there and help take shape to our final design. Then I'll be talking about the COVID-19 outbreak and how it delayed and hindered a lot of the quality of our project and results. Lastly, I'll be going into the final design, the items we will be delivering to JUMP since the end of the semester is here, as well as recommended future design changes for JUMP if they do decide to produce more smart ankle trainers for distribution to various OSF physical therapy offices. The JUMP Simulation Center is owned and operated by OSF Healthcare. JUMP specializes in innovation, education, and research for a lot of the OSF facilities. One facility employee who is a physical therapist, Kate Hulse, came to JUMP with the problem that was apparent in her physical therapy office. The problem Kate found was that when using wobble boards on patients who needed ankle rehabilitation, the wobble boards being used were not doing the job correctly. The wobble board being used in the physical therapy offices was the BAPS board. The BAPS board is not only very expensive, but it's very tedious to lug around with all the pieces and to set up and take down for various patients who had different needs. Another problem that was apparent not only in the BAPS board, but in the majority of all wobble boards on the market was that they do not give any automated feedback to the user or to the physical therapist. Oftentimes, Kate would actually have to kneel down on the ground and stick her fingers underneath the board in order to show patients what their range of motion goal was, and in turn pinching her fingers underneath the board. Our group's goal was to come up with one final working wobble board at the end of the semester that would give automated feedback to the user and to the physical therapist, have the ability to be transported without any kind of hassle or losing any loose parts, and be underneath the target price of $50 so that it would be relatively cheap if JUMP did decide to replicate our work and produce more smart ankle trainers for their physical therapy offices. Right away, our team dove right into working on the problem. One major way we went about this was utilizing brainstorming techniques. Our team had weekly meetings. Oftentimes we would meet in the makerspace and we would utilize a lot of the whiteboard space and open area to just express our ideas and characteristics of various wobble boards that could be used in combination to form prototypes that would then be tested to combat the problem. Even though we were only brainstorming ideas and characteristics that the wobble board might have, our group found that they could always be lumped into 2 categories: mechanical prototypes versus electronical prototypes, which both had their own pros and cons. For example, electronic components have to have batteries, but mechanical prototypes would be purely mechanical and only have limited feedback. After a few weeks of brainstorming, we had 4 prototypes take shape, and we felt they were at a good point in which our group could present to them at JUMP at our midterm presentation in order to gain feedback on what they thought would work and what they thought wouldn't work to fit the project scope. Our 4 prototypes consisted of the ankle cradle, which is in the top left, the wedge board, which is the bottom left, the ball game board, which is the top right, and the LED board, which is the bottom right, all of which gave automated feedback and were designed to have minimal drawbacks when used in the field. The first prototype that was presented to JUMP was the ankle cradle. This was unlike our other 3 prototypes because it did not closely resemble the traditional wobble board, but still did the same thing for the user, and that was to increase ankle range of motion and ankle strength. The frame would rest on the ground while the user sits or stands and puts one foot in the cradle. But unlike traditional wobble boards, one upside to this design was that it would be harder for the user to hyperextend their ankle by losing control of their range of motion or ankle muscles and going too far in any single direction. The cradle had 4 elastic attachments to the frame, which each had a force gauge attached to it. This would provide feedback to the user and to the physical therapist to show how much force the user is exerting in any direction, therefore giving feedback for progress for the user. The second prototype was the wedge board, and again, just like the one before this, was a purely mechanical design, just like the ankle cradle. The wedge board resembled the traditional wobble board with one small change, and that was the rails and wedges, which were mounted underneath the board. These wedges had 2 applications, first of which was to prohibit the user from hyperextending their ankle in any particular direction to prevent unnecessary injury while rehabilitating, just like the ankle cradle. But the second was that the rails would provide different adjustment levels for the wedges, which would allow the board different angles of tilt for different ranges of motion, therefore giving the feedback to the user when the wedge hit the ground, telling them that they hit their range of motion goal. The third prototype was the ball game board. This again resembled the traditional wobble board design, but this time there were 4 tracks carved out of the top of the wall, like top of the board, in each of their own directions, with a ball sitting in each of the tracks. The purpose of these tracks was actually to give the patient and the physical therapist feedback on how far the board was being tilted in each of the 4 directions. This would be apparent by having incremental steps, which would correlate to various angles of tilt of the board with that given direction, and the ball was the indicator on how far the board was being tilted in that radial direction. The last prototype we presented to Jump at our midterm presentation was the LED board, and unlike the other 3 prototypes presented, the LED board was completely electronical. We took the design of the basic wobble board and added a gyroscopic sensor, LEDs, and an Arduino board in order to give the feedback to the user. Our thought process behind this was that there would be a strand around the outside edge of the board. Inside the hemisphere on the bottom of the board would sit the gyroscopic sensor and the Arduino board. This would sense the angle of tilt of the board and then light up the corresponding LEDs for the direction of tilt. The feedback for this would be the color of each LED light. Different ranges of motion would have different corresponding LED colors. For example, 0 to 10 would be red, 10 to 20 would be yellow, 20 to 30 would be blue, and so on and so forth. This would give the user the feedback instantaneously and would also add some sort of level of gamification to the board so that they could meet their range of motion requirements for that day. The midterm presentation for our group was actually a very big stepping point in finding the direction for the rest of the project. Our presentation quickly turned into an open discussion and brainstorming session with the Jump team, and they got to voice their opinions on what they thought would work and what they thought didn't work. This actually gave our group a lot of very helpful information on what they thought the project should be, and even though we didn't get to meet with the members of Jump on a daily or weekly basis like some teams did, this gave a lot of feedback to us, and our process of the project so far was extremely helpful, and in the long run outlined how the final product would turn out and the rest of the direction of the project would be taken. On March 12th, St. Ambrose University decided to switch to online learning due to the ongoing COVID-19 outbreak. Due to this decision by the university, it left a big question mark on how our final project would turn out at the end of the semester. Not only having university equipment and resources really hindered our progress, but luckily each member quickly found their role on the team with what available resources they did have. Herb ended up drawing the short end of the straw here because he had a lot of equipment at his house for construction and assembly, and so Herb was also ultimately placed on the task of fabricating and assembling all of the physical products for the final design, as well as a lot of the electronic coding and assembly of electronic portions. Ethan and I assisted Herb as much as we could by having lots of FaceTime meetings with him and trying to brainstorm different ideas to come up with diagrams on problems on how to overcome certain issues. And finally, after some work, we were able to get our final design back on track, and it started to take shape. Based on Jump's feedback at the midterm presentation, our final design was a mix between the LED board and the ball game board. The LED board characteristics that would be apparent in the final design would be the LEDs, the Arduino board, and the gyroscope, but instead of having one LED strand go around the outside of the board, the members of Jump really liked the idea of having radial direction feedback, which was apparent in the ball game board. Having radial direction feedback would also give incremental progression feedback by having LEDs sequentially light from the middle of the board to the outside of the board, corresponding with different angles of tilt. Once we knew what characteristics to carry over from the prototypes to our final design, most of the work was actually already done. After some brainstorming and quick fabrication process, the final design would consist of 6 different components. The first of which being the acrylic disc that would sit on top of the board. The purpose of this disc was to allow the user to rest their foot on top of the board without having to worry of damaging LED strips or any other electronic components. Instead of using individual LEDs, the decision was to get LED strips. These LED strips already came put together and had some layer of protection and only really needed to be cut out to the desired length, and a few minutes of soldering a wire for a ground and a positive wire, which would then be hooked up to the Arduino board, was all that was needed. The wood disc was mainly just to hold everything together and give the majority of the support to the user. These divots that are carved out in the middle, starting from the center of the disc to the radial direction in 4 different directions, are what the LEDs would sit in, and then another divot would be carved out at a 17-inch diameter so that the acrylic disc would sit on top, protecting the LED strips and all of the wiring. Then all of the wiring would be routed through the middle of the board onto the Arduino board, which would be powered by a 9-volt battery and having the assistance of a breadboard for some of the wires and to hold the gyroscope in place. The housing unit was then attached to the underside of the board to hold all of the wiring and electronic components together, and to have available access to turn on and off the Arduino board by connecting and disconnecting the 9-volt battery. Then once the housing unit was attached to the bottom side of the wooden disc, a circle was routed out for the semi-hemisphere to be mounted on the bottom, which was then the pivot point for the board to rotate on. And that was all of the final product, and it was finally ready to be used. The items that we plan on handing over to Jump consist of the final report, which shows our progression and thought process through the entire decisions made throughout the semester. It also had the bill of materials, which outlines all of the raw materials used in case Jump does decide to reproduce our process in means of distributing the Smart Ankle Trainer to physical therapy offices throughout OSF. We also would provide the construction manual, which shows them how to construct the Smart Ankle Trainer, 2 Arduino code files, which would then be uploaded to the Arduino to run and operate the Arduino board, and desired feedback would be given to the user. And then lastly, we plan on somehow shipping the final product that is fully assembled to Jump so that they can test and hopefully use on site. A few future design changes that we did not have to implement would be audio feedback. This would not only allow visual feedback in the system, but would have some sort of noise to be played on the speaker when the user reaches their desired range of motion. This adds another layer of feedback so the user and the physical therapist know exactly what they're doing and how well they're doing it. Another design change would be the addition of more radial directions. This would just give the user and the therapist a lot more feedback than 4 directions. It would most likely be increased to 8, just increasing 4 more in each direction. And then lastly, due to COVID-19, we never really had the chance to test our product on any kind of patients. And so testing here would really help just polish up the product and help it be a lot more reliable. So even though this was an interesting semester, I would like to thank my group, the faculty, Dr. Lutz and Dr. Shi, as well as thank the Jump Simulation Center for giving us the opportunity to work on such an amazing product. I had a lot of fun and I really enjoyed working with my project group. Thank you all.